Hi, let's dive into teaching 2D arrays by solving two interview-level problems, one easy and one hard. For each problem, we'll cover the problem statement, approach, visualization, language-independent pseudocode, and time and space complexity discussion. The goal is to build confidence in handling 2D array problems for coding interviews. Introduction to 2D arrays. A 2D array is a grid-like structure with rows and columns, essentially an array of arrays. Think of it as a table, spreadsheet, or chessboard. For example, a 3x3 matrix looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. This has 3 rows and 3 columns. Elements are accessed using 2 indices: matrix, row, column. For instance, matrix 1, 2 is 6. 2D arrays are used in matrices, game boards, image processing, and more. Key operations include accessing elements, iterating through rows and columns, and initializing the array. Let's move to the problems to see 2D arrays in action. Problem 1. Easy matrix row sum. Problem statement. Given a 2D matrix of size m cross n, compute the sum of elements in each row and return an array containing these sums. Example. Input. Matrix equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Output. 6, 15, 24. Explanation. Row 1 sum equals 1 plus 2 plus 3 is equal to 6. Row 2 sum equals 4 plus 5 plus 6 is equal to 15. Row 3 sum equals 7 plus 8 plus 9 is equal to 24. Approach. This is a straightforward problem. We need to iterate through each row of the matrix. For each row, sum all elements in that row. Store each row's sum in a result array. Return the result array. Since we're only summing elements, we can use nested loops, an outer loop for rows and an inner loop for columns. Alternatively, if the language supports it, we could sum a row directly, but we'll stick to the loop-based approach for clarity. Imagine the matrix as a grid. Starting matrix row sum computation. Computing sum for row 1. Adding element at position 0, 0 equals 1. Adding element at position 0, 1 equals 2. Adding element at position 0, 2 equals 3. Row 1 sum equals 6. Computing sum for row 2. Adding element at position 1, 0 equals 4. Adding element at position 1, 1 equals 5. Adding element at position 1, 2 equals 6. Row 2 sum equals 15. Computing sum for row 3. Adding element at position 2, 0 equals 7. Adding element at position 2, 1 equals 8. Adding element at position 2, 2 equals 9. Row 3 sum equals 24. Final row sum 6, 15, 24. Output 6, 15, 24. Code. Function row sums, matrix. Get number of rows, m, and columns, n. M equals number of rows in matrix. Initialize result array to store row sums. Result equals new array of size m. Iterate through each row. For I from 0 to m minus 1. Row sum equals 0. Some elements in row I. For j from 0 to o, n minus 1. Row sum equals row sum plus matrix, ij. Store sum in result. Result, I equals row sum. Return result. Time and space complexity. Time complexity. We visit each element in the matrix exactly once. With m rows and n columns, we perform m cross n operations. Thus, the time complexity is O, m cross n. Space complexity. We use a result array of size m to store row sums. No additional significant space is used. Thus, the space complexity is O, m for the output array. If we exclude the output as it's required, the auxiliary space is O, 1. This problem is great for practicing basic 2D array traversal. Let's tackle a harder problem next. Problem 2. Hard spiral matrix. Problem statement. Given a 2D matrix of size m cross n, return all elements of the matrix in spiral order, clockwise, starting from the top left. Example. Input. Matrix equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Output. 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. Explanation. Traverse the matrix in a spiral, right down, left up, repeating inward. Approach. This problem requires traversing the matrix in a spiral pattern, which is trickier because we need to track boundaries and direction changes. The idea is to define 4 boundaries: top, bottom, left, right. Traverse in 4 directions: right, across the top row, then increment top boundary; down the right column, then decrement right boundary; left, across the bottom row, then decrement bottom boundary; up the left column, then increment left boundary. Repeat until boundaries cross, that is, top greater than bottom or left greater than right. Handle edge cases. Empty matrix, single row, single column. We'll use a result array to store elements and update boundaries after each direction's traversal. Let's visualize spiral order traversal. Moving right. Adding element at position 0, 0 equals 1. Adding element at position 0, 1 equals 2. Adding element at position 0, 2 equals 3. Adding element at position 0, 3 equals 4. Moving down. Adding element at position 1, 3 equals 8. Adding element at position 2, 3 equals 12. Moving left. Adding element at position 2, 2 equals 11. Adding element at position 2, 1 equals 10. Adding element at position 2, 0 equals 9. Moving up. Adding element at position 1, 0 equals 5. Moving right. Adding element at position 1, 1 equals 6. Adding element at position 1, 2 equals 7. Output 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. Pseudocode. Function spiral order, matrix. Handle empty matrix. If matrix is empty, return empty array. Get dimensions. M equals number of rows in matrix. N equals number of columns in matrix. Initialize result array. Result equals new array. Initialize boundaries. Top equals 0. Bottom equals m-1. Left equals 0. Right equals n-1. Traverse until boundaries cross, while top less than or equal to bottom and left less than or equal to right. Traverse right. For j from left to right. Append matrix, top, j, to result. Top equals top plus 1. Traverse down. For I from top to bottom. Append matrix, bottom, right, to result. Right equals right minus 1. Check if more rows remain. If top less than or equal to bottom. Traverse left. For j from right down to left. Append matrix, bottom, j, to result. Bottom equals bottom minus 1. Check if more columns remain. If left less than or equal to right. Traverse up. For I from bottom down to top. Append matrix, I, left, to result. Left equals left plus 1. Return result. Time and space complexity. Time complexity. We visit each element exactly once. With m rows and n columns, we process m cross n elements. Thus, the time complexity is O, m cross n. Space complexity. We store all elements in the result array, which is m cross n. Excluding the output, we only use a few variables, top, bottom, left, right, so the auxiliary space is O, 1. The total space complexity, including output, is O, m cross n. This problem tests boundary handling and direction changes, making it a great interview challenge. We've covered 2D arrays through 2 problems. Matrix row sum, a simple traversal problem to practice iterating over rows and columns. Spiral matrix, a harder problem requiring careful boundary management and direction changes. Both problems reinforce how to navigate 2D arrays and think systematically. For practice, try variations like summing columns or printing the matrix in reverse spiral order. I hope you get the approach to solve 2D arrays problems. Thanks for joining today's session.